Hey guys, so in this video we're going to discuss how certain disturbances like volume, pressure, and temperature affect a chemical system at equilibrium based on LeChateliers principle. So in the previous video we discussed how changes in reactant and product concentration affect a reaction equilibrium. Using LeChateliers principle, we saw how a chemical system will act to regain equilibrium after this disturbance. Now we're going to discuss how a system regains equilibrium after changes in volume and pressure, which have opposite effects, and temperature. Changing the volume of a reaction mixture in equilibrium can cause a disturbance and result in a response in the system to regain equilibrium. If we change the volume of a reaction system, the pressure is also affected because these quantities are inversely proportional. In other words, if we increase the volume of a reaction mixture, we are decreasing the pressure, and vice versa. Recall that the pressure is the force exerted by gas molecules. This means that more gas molecules lead to a higher pressure. Therefore, in order for a system to regain equilibrium due to a change in volume and subsequently pressure, the reaction will shift based on the number of gas moles on the reactant or product side of the reaction. For example, if we decrease the volume of a reaction mixture at equilibrium, we are increasing the pressure of the system. LeChateliers principle describes how the system will react to this increased pressure and try to reduce the system back to its initial pressure. So, the system will shift to the side that has the lower number of gas moles in order to decrease the pressure. Oppositely, an increase in volume leads to a decrease in pressure because less force is exerted by the gas molecules. Therefore, the reaction will shift to the side with more gas moles in order to increase the pressure. So it's important to note that if a reaction has equal number of gas moles on both sides, then the equilibrium will not be disturbed by a change in volume. Additionally, adding an unreactive or an inert gas such as a noble gas like argon to the system, this will not disrupt the reaction equilibrium. This may seem odd because the overall pressure of the system does increase, however the partial pressure of each component in the reaction mixture remains constant, therefore having no effect on equilibrium. The effect of temperature upon a chemical reaction at equilibrium depends on the enthalpy of a reaction. Remember that a negative enthalpy represents an exothermic reaction, indicating that heat is being lost from the system. Conversely, a positive enthalpy represents an endothermic reaction, indicating that heat is being absorbed by the system. We can treat heat as a reactant or product in the chemical reaction. Therefore, the addition of heat to an exothermic versus endothermic reaction will have different and in fact opposite effects. Now, unlike changes in concentration, a change in the temperature of the equilibrium mixture changes the equilibrium constant according to this equation. The ln of K is equal to the negative enthalpy over R times the inverse of temperature plus the entropy over R. And this equation is analogous to y equals mx plus b. So therefore, a plot of 1 over t versus the ln of k, which represents x versus y, this can be graphed to obtain a straight line. And this equation helps us to understand the relationship between the equilibrium constant and temperature as a function of enthalpy. For example, note the exothermic reaction where heat acts as a product in the chemical reaction. If the temperature is increased, heat is added to the system, causing an increase in the amount of product that is in the system. Now, to regain equilibrium, the system will shift to the left in order to decrease the amount of product present, subsequently increasing the amount of reactant. Therefore, the equilibrium constant is decreased. Now remember that a plot of x versus y, so 1 over temperature versus ln of k, is going to give us a slope that's equal to negative delta H over R. But if we have an exothermic reaction where delta H is negative, this is actually going to result in a positive slope. And this means that the equilibrium constant increases with decreasing temperature. So this explains why we see a decrease in the equilibrium constant as the temperature increases for an exothermic reaction. In this example, the reaction is endothermic, therefore heat is absorbed and can be treated as a reactant in the chemical reaction. So if the temperature is increased, heat is added to the system, causing an increase in the amount of the reactant that is in the system. Notice that this is the opposite effect from when heat is added to the previously discussed exothermic system. Now, to regain equilibrium, the system will shift to the right in order to decrease the amount of reactant present, subsequently increasing the amount of product. Therefore, the equilibrium constant is going to increase. So again, if we think about this plot of 1 over temperature versus ln of k, our slope is going to be equal to negative delta H over R. And so this is going to result in a negative slope. This means that the equilibrium constant increases with increasing temperature. Okay, so let's try an example to make sure that we understand all of these concepts. So we have the following reaction, which is exothermic, meaning that heat is a product. We're asked to discuss the effect of 3 different scenarios, and the first scenario is the effect of decreasing the temperature of the reaction mixture. Now, if we decrease the temperature, this means that we're going to be reducing the amount of product that is in the system, and in order to counteract this, we're going to have to increase the amount of product that's in the system by shifting the reaction to the right. Now remember, in this situation, we're also going to have an effect on the actual equilibrium constant. So remember, for an exothermic reaction, the slope is going to be equal to the negative delta H over R, therefore resulting in a positive slope, which means that temperature increases as the equilibrium constant decreases. So in this scenario, if we're decreasing the temperature, we're actually going to be increasing our equilibrium constant. Now in the second scenario, we want to know what the effect of adding additional Xe gas or xenon gas to the reaction mixture. What is that effect? So this is a noble gas, which means it is very unreactive or inert. So remember that this is going to cause an overall increase in pressure of the system. However, the partial pressures of the reaction components are going to remain constant. So this means that there's going to be no effect on the system. The final scenario, what happens if we decrease the volume of the reaction mixture? So remember that decreasing the volume is going to be related to increasing the pressure because the two are inversely proportional to each other. Now if we increase the pressure, this means that we need to figure out a way in which to decrease the pressure back to its initial pressure. So in order to decrease the pressure, we're going to need to decrease the number of gas moles. So the reaction is going to shift towards the side with less gas moles. So if we look at the reaction, our reactants have 3 gas moles. We have 2 coming from SO2 gas and 1 coming from O2 gas, whereas our product has 2 gas moles. Therefore, we're going to shift towards our products, and the reaction is going to shift to the right in order to regain equilibrium. So overall in this video, we've learned how a system at chemical equilibrium will regain equilibrium due to disturbances in concentration, volume and pressure, and temperature due to LeChateliers principle.